Okay, let's talk about ungrounded systems. Now, the NEC defines an ungrounded system as a system not connected to the earth. If you take a look at this winding, it is shaded. That is the separately derived system. And this system has no electrical connection or conductive connection at all to anything that has a connection to the earth. So that is what we're talking about, an ungrounded system. Now, one of the problems with an ungrounded system is that equipment can be easily damaged from transient overvoltage caused by lightning or restriking ground faults. Not only that, but there are other cases. So let's take a look at this. Here's a winding with no connection to the earth. Here are insulated conductors. Lightning event outside creates a magnetic field. That expanding and collapsing magnetic field induces and puts pressure on the conductors, which then puts pressure on the system, and that energized charge is attempting to get to the earth. And so it can cause a discharge, and what it does is it causes premature failure of electrical equipment. Now, there's a book written by Don Beeman in the 50s for Industrial Power Systems Handbook. And just to kind of put things in perspective, and I'm not trying to be disrespectful to engineers today, but in the 50s, these guys were engineers. We're talking serious engineers when it relates to power. But understand what happened in the 50s and the 40s, and that's before transistors, right? Before electronics and computers, the cell phones and fax machines and all these electronic things. When they went to engineering school, they went to power engineering. They studied engineering as it relates to power. Once a transistor came out, all of a sudden, today's engineering schools, and I think there might be a trend going the other direction, but it all went into electronics. And I think the IEEE was IEE, and then it became IEE, right? And then it became electronic, and then it became electronic was added inside there. So now, many of the engineers today, when they go to college, or the engineers coming out of college today, for all practical purpose, they have no clue what they're doing when it comes to electrical power. I mean, none. They don't know anything about grounding and bonding. They really don't know anything about grounding electrical power systems, distribution systems. And so these guys are coming, but they don't know anything about cell phones, but they know they're very smart people. Then when they get out of engineering school, they go into the area that they're specializing in, and they're so smart, they get the information, and then they go with it in that way. But back in the 50s, this is when the guys had the real base. Here's what Beeman was talking about. Here's what he says. Because of ungrounded systems, you have overvoltage sources, and he lists 8 different causes of events. There are many varied sources of overvoltage of sufficient magnitude to be damaging to the insulation of AC industrial power distribution systems. In this chapter, the mechanisms by which the more prominent overvoltages are created will be described and preventive measures suggested. Treatment of the following will include. So this particular chapter, and I bought the book. I know tomorrow you guys can come to my house tomorrow so you guys can see the book there. And so because of ungrounded systems having overvoltage, it just created problems. Now, there's advantage to an ungrounded system. One of the advantages to an ungrounded system is that if you had an assembly line and all of a sudden one phase goes to ground, well, nothing happens because the only way you can clear a fault is that fault current gets to the source, and since nothing is grounded, then there's no way for the fault current to get back to source, or really bond is the right term inside here, until what? Then once you get one phase going to fault, that now becomes a corner grounded system, which we're going to talk about. And the danger is that if we don't clear that ground fault of an ungrounded system, that there could be a second phase that would take a fault, and now you have a phase-to-phase 480-volt fault, and that can be a very serious application. So we have a problem with ungrounded systems because the system can be unstable as it relates to equipment failure because it builds a capacitive charge. You have restriking ground faults, you have a ferroresonance, and a lot of it, and this thing could cause the energy on those conductors on that insulated system to be 6 to 8 times the voltage rating of the conductors. Well, you take 6 times 600 volts, that's what? 3,000 volts, 3,500 volts. At that point, the insulation can't sustain it, now but discharge. And more than likely, it doesn't even have to go that high. You start getting motor windings, you start getting relays, you start getting electronic equipment, you start getting the tolerances much closer. So there's just an inherent problem with overvoltage and equipment failure for ungrounded systems. Now let's take a look at the code. The code requires that if you do have an ungrounded system, that you have some kind of ground detectors. That's 25021B. And here's a simple way of doing it. Taking 3 light bulbs, connecting to each of the phases, and if you have this point here, well, I put a 240 volt bulb here because that voltage, this is up. Secondary is going to be voltage to, let's see, would I have any light bulb working here? Would a light be lighting up here? On the normal condition?
Normal conditions, yes.
Oh, that's right, because we're going from this one phase here through the light bulb going inside here.
Right.
So the lights would be all on as long as there's not a ground fault.
Somewhat dim,
Or
but they're
dim,
on.
right, just got to. But once you have a fault, once one phase goes to ground, now the voltage between the other 2 phases relative to that reference point. Now, see right now, this voltage from this point to the case, there is none, right? From this,
Well, it's 120 if you have,
because we put the light bulbs in there?
because you put the light bulbs in there.
Ah, so we're getting 120 on that one, if it was a,
122.08.
oh, we are going to get 120 because we put the light bulb there.
Right.
It does give us, is it still an ungrounded system with the detectors in there?
It's an ungrounded system. You got to be real careful on that one because it's a very weak ground. It can't really do anything.
Right.
But it
Yeah.
is a grounded
Because of the light bulbs.
because of the light bulbs.
Okay, so it requires ground detectors. Now, I'm not sure if you can put light bulbs today. They sell ground detecting devices, so that's what would be used. All right. Now, if you have an ungrounded system, the code requires us to put a label identifying what the voltage is between conductors. See, without having any kind of direct connection in any way through light bulbs, there is no voltage between any of these one phases to the enclosure. So therefore, you can't say there's any voltage to ground. The voltage is only between the conductors. That's a code change. All right. Anybody want to say anything about ungrounded systems? More than likely, they're not being installed, probably, unless you had a facility that already was ungrounded. This is something that was done more in the 40s. You have to maintain it. You're probably going to maintain an ungrounded system. One of the dangers of an ungrounded system is that you could have a 480 volt or 240 volt ungrounded system, and then utility changes their transformers. And that's going to be very, very careful because they could change their transformers so that it then becomes a grounded utility system, but yet the premises wiring were designed to be installed per an ungrounded system. Steve.
One of the dangers with the ungrounded system is if people get sloppy and work on them touching a hot conductor and touching ground because there is no ground path to cause electrocution until someone else does the same thing with an opposite phase, then you're both going to get burnt.
So if 2 guys are working in
Yeah.
2 different spots and one guy touches the phase conductor, touches the equipment
Yeah.
case, you can't get shocked because it's ungrounded, but then somebody else makes a connection, or it happened to be a
Or
ground fault.
A fault, yeah.
Then we have a corner grounded system.
And I heard that years ago people used to do that.
All right, I'm going to close up ungrounded systems. It's not a common application. I'm sure if you go on the internet and you want to do any kind of research on ungrounded systems, you're going to get lots of information. There is inherent problems with ungrounded systems, and it's not something that's probably installed today. I've heard that utilities might not even allow you to have a new system, an ungrounded system. So I'm not sure about that. Number 2, point I want to cover, is a grounded system. This is what we do every single day. This is the 98% of applications here. What do? You take the XO and you make a connection between the XO, this Y configuration, and therefore making a connection to the case. And then we're taking this system, and more importantly here, we are grounding it to some conductive body that extends the ground connection. By having a system that is grounded like this here, back in Beeman's book talking about all these overvoltage conditions that could take place, this ground connection from the case, from the system itself, this allows a method for that charge, for restriking ground faults or ferroresonance or induced charges from lightning, whatever it might be, that energy can be displaced because it's trying to get to the earth. And that's why we've chosen to go with grounded systems. There's a problem with a grounded system, though. One of the problems with the grounded system is now that the system is grounded, you can touch a hot wire somewhere, and now you can get killed because current can travel through you. You're standing on something conductive, the earth or concrete, whatever it is. Electrons can get back to source. So a grounded system is inherently more dangerous. Another disadvantage of a grounded system is that the moment the first phase goes to ground fault or faults, you immediately open up the protected device. Well, that's good because you want to clear a fault, but it's bad if you have an assembly line because now everything stops. So now you're making the compromise because we really don't want to turn things off when there's a fault. We want it to run, but we don't want to have equipment failure. So I guess we're going to go with a grounded system. But when you go with a grounded system, now you can kill people. And now the first fault, you clear the protected device, and now we have things turning off. And so that's one of the problems with a grounded system. Eric, were you going to say something?
Yeah, I just want to point out, because this is such a good graphic right here, it shows it very clearly, that in a separately drive system, you have your choice to bond either the transformer or the first disconnect. This particular graphic shows where the transformer is bonded to the case, but we could just as easily have bonded the first disconnect.
Right. Exactly right. All right. Let's go to this graphic here. On a grounded system, there's an informational note in 254A1, and it says this: the grounding electrode conductor should be no longer than necessary, and you should avoid unnecessary bends and loops. And the reason being is this conductor right here is not carrying fault current. This conductor right here is carrying high frequency transient energy to the earth. The size of the conductor really is unimportant. What really matters is the length of the conductor, because high frequency current travels on the outside of the conductor. So you really want your grounding electric conductor to be as short as possible. You probably would be better off running 6-gauge wire from a 2,000 amp service to 2 ground rods than you would be running 500 thousandths or 3/0 or 4/0 or whatever it is, 50 feet or 100 feet over to some special ground bed. You got to realize we're talking about high frequency discharging of energy, a little low frequency because you have static electricity, what have you. So people are thinking about the grounding electrode as somehow it's carrying a fault. If you go to 25066, it tells you if you're going to ground rod, no larger than a 6-gauge wire. B says if you go to a concrete encased electrode, no larger than the concrete encased electrode conductor that would be required, which would be 4-gauge. Ground rod, 6-gauge, concrete encased electrode, U for ground, 4-gauge. Why? Because it's just discharging this high frequency energy to the earth. So you want it as short as possible. Wire size is not important unless you're not going to be going to a ground rod or rebar. And then, of course, you go to table 250.66. Now, what systems are required to be grounded? Well, if you ever want a 120-volt circuit, then you have no choice. You have to ground one of the conductors. So if you have a 2-wire circuit that's 120 volts, line to neutral, then one phase has to be grounded. If you're going to have line to neutral 120 and 120, well, this is a typical 480 to 120, 240, well then the center point is going to be grounded. If you have a Y system 120, 208, since you have line to neutral loads, you have a neutral conductor in there, then you have to ground it. So let me just review this with you. You have ungrounded systems and you have grounded systems. An ungrounded system can be used in all these areas, except there are certain applications where you have to have a grounded system. Anytime you go in line to neutral loads, 120-volt circuits, 277, from a 277, automatically you have to ground that system. So that's one of the things you realize. A grounded system allows line to line and line to neutral loads. An ungrounded system does not give you that opportunity. It can only be phase-to-phase load. So that's something to take in consideration if someone was considering about what are the different options here. Let's go back to our graphic. So since this is a Y secondary and it's a 120, 208, well, you have line to neutral loads. It has to be grounded. Here is a delta high leg system, and because we have line to neutral loads, the system has to be grounded. So if you want line to neutral loads, you have no choice. You're going with a grounded system. There is no option. I'm done talking about grounded systems. It's a short thing. You want to know more about grounded systems? I'm sure you can go on the internet and you're probably going to find grounded systems. More than likely to say my code forum. So probably it's going to end up going to my website. Okay. Number 3, delta-delta corner grounded systems. This is not something that's very common. It's mostly used in old industrial applications in Chicago and New York and Philadelphia warehouse areas. Let's assume that the secondary, in this case here, could be 240-volt line to line or it could be 480-volt line to line. That's not important. You take the system, which is the separated drive system, and you ground one corner. That means that this is a corner grounded system. That means the conductor that's leaving that, actually, we wouldn't even call this line 3. We would call this a grounded conductor. So it's not, well, it's a third phase. So in that case, it'd still be a third phase. So now what's the advantage of a corner grounded system? Well, the advantage is this. If we had an ungrounded system, which is permitted by the code because we're not supplying line to neutral loads, right? And everything is going great, but we're finding out, what are we having a problem with ungrounded systems? What? Ungrounded systems have a problem of over voltage, right, Eric? That's our problem
Yep.
with ungrounded systems. We're like, oh man, what are we going to do? I know what we can do. Let's corner ground one phase, which is fine because we're not supplying line to neutral loads. We're supplying line to line loads. The only key that we got to be careful on is the grounded conductor has to be identified in accordance with 200.6 in the code. And not only that, but let's go to the code book also. Get your code book out. Go to 240.22 about the grounded conductor. 240 has to do with overcurrent protection. It says this: no overcurrent device shall be connected in series with any conductor that is intensely grounded unless one of the following conditions are met. And number one is the overcurrent device opens all conductors of the circuit, including the grounded conductor, and is designed so that no pole can operate independently. That means I'd have to put what then? A circuit breaker if I plan on switching the neutral. Is that right? So I could use a 3-pole circuit breaker on a corner grounded system. One phase is going to be white, and the other 2 phases are going to be identified, and however we're going to identify for the systems. Eric?
Well, and if, let's just say that this were already installed and you decided to ground it, and you already were in a fuse disconnect.
Hold on. Let's go with this example, the graphic you're saying here. So I just want to bring the picture you're talking about. You're
Okay.
saying we have this, everything is great. When this is black, red, whatever colors, all black, and then breaker, simultaneous, and then
Breaker simultaneous is fine, but now let's say that that disconnect is fuses, 3 individual fuses.
oh,
Okay, now if that's 3 individual fuses, and if you ground that bottom left corner of the delta and follow that line over to the fuse holder, you would replace that fuse with a slug or a bar.
okay. Or you take it off of the bus and you go right
And you
on to the
connect
neutral.
it together.
You connect it to the neutral bus.
Right.
Well, you don't have to connect it. No, you just connect it together.
You connect it together.
Right. You don't have to terminate to a neutral bus at all. You run the wire. In other words, I could bring the grounded conductor right through, take it right to my load. I don't have to have it. It's a grounded conductor.
Right.
Not a neutral, because it doesn't work that way. All right. Let me see if there's anything I want to say about the corner grounded delta systems. Now, as I got feedback on our streamers, I was like, Mike, I had a lot of corner grounded delta system. They never identified that grounded conductor white. I don't doubt that. Maybe the grounded conductor identification was something that was added after all these systems were installed. So you have 2 choices. Take the 3 phases off the corner grounded system and put it into a 3-pole breaker, or put it into a 2-pole breaker, or put it into a 2-pole fusible disconnect.
Right.
So those are your 3 options. If you choose to switch the grounded conductor, it needs to be in a 3-pole breaker. If you say, forget about that, I just put a 2-pole disconnect on there, and I'll just run the neutral conductor, I'll run the grounded conductor right through the disconnect, or if you want to terminate it on the neutral bus in those disconnecting means, but do not install the bonding jumper between the neutral and the enclosure. Let's talk about advantages to a corner grounded system. Well, it's grounded. Right? Takes care, and like Eric, you said, hey, we had ungrounded systems, we had problems. So maybe the corner grounded delta system was more of a derivative of, like, all these systems are ungrounded, having these problems. Somebody came up with the idea, let's just corner ground it, and now we have what? It's not connected, they're on fusible disconnects, right? And they're not white. And that was maybe the history of the problems that we have. I'm done with corner. Yeah, Stephen.
See a lot of installations on these kind of systems where you have a remote location, just need a 3-phase motor, like oil rigs or well pumps or irrigation pivots, where they just run a corner grounded delta out there. They don't need a neutral. All they need is power for that 3-phase motor.
Makes sense. I mean, makes total sense. 3-phase, right?
Yep.
Corner ground 1 phase, put
And a
2-pole
lot of
breakers,
times-
put
a lot of
2-pole
times it's-
disconnects.
A lot of times it's open delta, and the power company saves money on one transformer.
Number 4 point I'd like to discuss, high-impedance grounded system. Now, to me, this is the bomb. This is the way it should be. This is the coolest thing. I know, and this is really complicated. Watch what we have here. This high-impedance grounded system means that you take the system itself, and you're actually putting a resistor in series. So this is no longer a solidly grounded system, but we're putting a resistor between the exo and the case of that transformer, and then the case of the transformer is going to be grounded. Even though they talk about this being a high resistive grounded system, and in fact, what does the code call this? 250.36. Does it call it a high resistive neutral system?
Didn't your impedance grounded?
Just resistance grounded. Let's see.
I thought they called it somewhere a neutral grounded system. A high impedance neutral. 250.
36,
Yeah, 250.
page 116.
High impedance, right. Neutral, grounded neutral system. Well, that's what I thought. High impedance, I'm going to read it. High impedance grounded neutral system is in which a grounding impedance, usually a resistor, limits the ground fault current to a low value for three-phase AC 480 volt systems if all of the following conditions. That means that this is a 480 volt system. So let's hold that concept there. This is 480 volts. Now, high impedance grounded systems are 480 volts. You're using a resistor in place of solid, and this resistor is designed to limit the current under a fault. Watch this. When you have a fault here, now fault current comes here, it returns back to the source. This resistor typically would be rated 277 ohms. Because this phase going to the case, going back to the source, which is resistive grounded, that voltage between this winding right here is going to be 277. That limits this current to 1 amp. However, if you have a larger and larger and larger systems, the larger the systems you have what is called the charging current. Just simply alternate current moving out and moving in and moving out, moving in, creates a capacitive charge on the conductors. And that charging current could be maybe up to 3 amps. Well, then if you use a 277 ohm resistor and you get 1 amp, 3 amps of charging current, well, then you're going to have that resistor. It's going to detect the more than 1 ampere. It's now going to set off the alarm that you have a ground fault. So what they then do is they move the ground fault detector higher up, and they can set that resistor so that you can carry 3 amps. You might even decide, no, our system is so big, I believe the maximum, and I don't think that's covered in the code, I believe the maximum typically that's done for the charging current, and that resistor is designed to carry no more than 10 amperes. I tell you, if you want to know more about high resistive grounded systems, and I'm sure there's other manufacturers, I'm sure Square D, Eaton, Cutler Hammer, and other manufacturers, but iGuard is an organization and a company that really, really focuses on high resistive grounded systems. They have great training material, great information that will help you understand about, well, how do you size that resistor and how does that work out? And they'll give you that information. But let's go back to the graphic to understand. We still don't understand what we're talking about, so let's do this a little bit more. Ready for this? Now, this is a 480 volt phase-to-phase application that when you have one phase go to ground, look at the fault current. 1 amp maybe, 3 amps, 7 amps, possibly as high as 10 amps. Guess what we don't have? We don't have the danger of an arc flash blast hazard. Now, you would have it if one phase goes to ground and then nothing is fixed. The alarm goes off. Nobody fixes that single phase ground, and then you have a second phase that goes to ground. Now you have a phase-to-phase 480 volt fault, which is devastating. And when you get a 480 volt fault, if you have an ungrounded system and one phase goes to ground, nothing happens. It becomes a corner grounded system. And if you take the second phase to go to ground, now you have a 480 volt phase-to-phase ungrounded system, becomes a grounded system. Second phase fault requires phase-to-phase fault. 480 volts. When you have a 480 volt fault, it does not, the voltage goes from 0 to peak to 0 to peak, 0 to peak. 120 volt, when it goes to 0 to peak, it arcs. It extinguishes itself when it gets near the 0. And then it arcs, then it extinguishes. 277, 480 volt, anything over 350 volts, I think, peak. The arc goes, it doesn't extinguish itself. It just keeps, it now becomes a high impedance arcing fault. So the protected device now sees a phase-to-phase high impedance arcing fault, which is not high enough, however, for the protected device relays to be able to open. And I've seen this at Texas Instruments, TI, in their facility. They had burnt down this huge amount of switch gear. Arcing fault started, just kept going and never stopped. So what did they do? They changed all their systems to high impedance grounded systems, because here's what it gives you. It's a grounded system. That 1 ohm resistor allows you to do what? Take the energy, the restriking ground faults, the ferroresonance, the induction from lightning, and other applications. That is able to do what? Because high frequency, go right through that resistor and get bled. So you get the advantages of a grounded system, but you also get the advantage of an ungrounded system, is that when the first phase goes to fault, it doesn't open a protected device, sets off an alarm. Now, the disadvantage to a high impedance grounded system is that you cannot supply line-to-line loads. This is all contained in 250.36. So you can't supply line-to-line loads. So if you want to have 277 480 volt lighting or 120 208 volt circuits, well, then you're going to have to take and add another transformer on the load side of the high impedance system to supply those type of systems. And it's the coolest thing. Here's your resistor there. The fifth thing I'd like to talk about as it relates to transformers is backfeeding a transformer. That's when you take a transformer that's a 120 208. I'm sorry, that's a 277. No, that's a 480 to 120 208, and you actually backfeed it. Now, let's go through the rules that apply to this. Number one, we have to disconnect this neutral in this graphic because you cannot connect a neutral on the primary side of this Y configuration if you're going to backfeed a transformer. That's all part of the equipment manufacturer's instructions. So that's number one. Number two, the transformer has to be specifically identified that it's permitted to be backfed. Transformer can be supplied at the marked secondary voltage, provided the installation is in accordance with the manufacturer's instructions. This is done all of the time. And by the way, Mike, see this grounding right here? Get the grounding out of here. You don't ground the primary, and you don't bring a neutral to the primary when you backfeed a transformer. Let me tell you when you want to do this. Not when you want to do this, when you do this. You are at a 120 208 system. You got 277 480 volt lighting in the parking lot, and you want to connect the lights. So what do? You backfeed a transformer. Now you have an output of what? 480 volt ungrounded. What do we have to do when you have an ungrounded system? Got to put a ground detector. Yes, sir.
You said 277 volt parking lot lights. Where's your 277?
I'm sorry, 480.
Okay, gotcha.
I'm sorry, my mind. So 480 volt parking lot lights. So I do what? Because the circuits are so long, more than likely most lighting, and correct me if I'm wrong, parking lot lights, they can connect to a lot of different voltage levels, right? So what you want to do is you're going to say, hey, listen, let me give it an ungrounded 480 volt system so I can have what? Smaller conductors because the voltage is going to be up, the current's going to be down. The only thing you got to be careful on that is that when you backfeed a transformer like this, you have to make sure that because you have an ungrounded secondary, you have to have ground detection. And we covered that in ungrounded systems back in 250.21. We'll add it to the graphic here. So you need to have ground detection. 250.21, I think it might have been D. So this is perfectly fine. It's done all the time. And obviously it's safe because it's an ungrounded system.
I think it'd be a lot safer if we corner grounded it, though.
Why?
You're going to be running it out to those lamp poles out in a public area where people could get around them, and detection or not, if one of those phases went to ground, I don't know.
Say that again to me.
Well, particularly if you're going to have it out lamp poles where it's
Yeah.
publicly accessible,
Right.
and you got kids running around, they can be around those light poles and so on. I think a grounded system would probably be safer
But if it was ungrounded, then the kids couldn't get shocked, right?
until one phase went to ground.
Well, then you're grounded. So we're one step away from getting hurt. You're saying, let's remove that one step away. Let's ground it in the first place. Now you have a face-to-face fault, and you can kill people because it's grounded. If you go ungrounded, then you can't have a face-to-face fault because you got to wait for the second fault to go.
Yeah.
Now, that doesn't mean on an ungrounded system you're not going to get shocked because we have what? We have a charging current that's taking place. You have that charge that's in there. So even though it's an ungrounded system, you will be able to get touching a phase conductor and get a charging current.
Okay, my recommendation is before you just go ahead and do this, you have to understand that here we have a standard transformer, and you just mentioned that they're going to need to purchase a ground detector. And so for the ungrounded system. And so you can buy a step-up transformer from manufacturer, and you know that chances are the price of a step-up transformer might be cheaper than a standard transformer and a ground detector.
Without a doubt, the best thing would be to know in advance what you need. Get a transformer that's going to be a 120 208, 480 volt, specifically for this application. But a lot of guys, they need to get it now.
Right,
And they don't have the
exactly.
time to wait for that. But what they have been doing is they have been backfeeding it. Manufacturers will market, clearly market the instructions, but they haven't been putting ground detectors.
Right.
So now, if the guy does this, doesn't put a ground detector, inspector comes out and says, whoa, whoa, what's going on here? Then the solution is what? Corner ground it, right? And then do what? And then use a grounded conductor, put it white. So you might end up getting to a corner grounded because you don't want to waste your money with a ground detector. So we might go there. Or maybe they make better systems to apply for the 480 volts parking lot lighting, because it's a small transformer you want to get. Michael.
Is it important that you have a balanced load on that 480 volt side? What happens if it's all over the place? What happens to the primary?
You're saying...
I mean, I can see that for feeding a motor that you needed to take and had to, run a motor, specific load, balanced load on the 480. But now you have parking lot lights that it's very difficult to balance all those because they're on the different phases.
I'm not aware anywhere, whether it was a delta or a wide delta, that I have to balance my phases, that would have had anything significant. And if you had parking lot lights, more than likely you're probably putting it into a 3-pole panel, and you're getting face-to-face breakers, and you're going out there. But you might have one circuit that has more lights than the other, and I don't think the slight imbalance between one circuit, A to B, B to C, A to C, is going to be a material factor that, like, oh my gosh, you're up by 5% or 50%. So, no, I don't see any imbalance being an issue at all. Okay. Now, we're not getting into it, but we could easily have balanced out these loads and then go back to the windings. And I think, well, here, let's put it this way. If this was a 45 kVA, let me give you this, okay? The most you can have on any one phase would be how much? 15. So you couldn't put 25 kVA on line 1 and line 2, right? And then put 10 on line 2 and line 3, and line 1 to line 3. So, because that would, of course, translate itself to the winding. But I think that probably would have happened almost in all cases. You got to make sure you balance your transformer winding. So I don't think a slight imbalance, but you couldn't exceed any one phase. So I'll go with that. But it wouldn't be any different in any other system. All righty. I think that's the last of the 5 points I want to make. But I got some notes here. Some guys, streamers, have given some points. And let me give you what I got here. Ungrounded systems. Some interesting uses of an ungrounded systems. One was one of the guys brought out about mines dealing with explosives. Might be a good idea to put an ungrounded system on an explosive. Of course, ships are ungrounded systems. One time I know of a guy who they ran ungrounded systems in a forest. Because, Mike, we don't want to have a grounded system. These are higher voltage lines. We don't want to put a grounded system in a forest because one phase goes around, all of a sudden you burn down the forest. So you have an ungrounded system. You, even on an ungrounded system, even though you can't get killed probably by touching a phase conductor because it's ungrounded, you still have a capacitive charge. So you never want to be talking, you never want to work on anything hot. 70E always applies in every application, so don't imply that. On a resistive grounded system, the first phase, you will not have an arc blast, but on the second phase fault, you will have an arc blast. So I don't want to give the impression that, oh, well, resistive grounded system is you're okay, you can work hot. No, you can never work anything hot, period. 70E. 240.85 talks about circuit breakers being used, 2-pole circuit breakers being used on a corner grounded delta system, that the breaker has to be specifically marked single phase / 3-phase. So if you're going to be putting a 2-pole breaker on a corner grounded delta system, it's going to have to be identified for that application. It's something you might not be aware of. Now, what that means is that the breaker is going to be rated for that phase-to-phase voltage. 3-pole breakers are automatically rated for phase-to-phase as well as phase-to-line faults at the higher voltage. That's why it's going to be a straight rated breaker. So 3-pole breakers, you're always fine to put it on a high leg delta system. 2-pole breakers, be careful because you can't use a 120/240 volt 2-pole breaker on a high leg delta system. not highly, on an ungrounded delta system, because if one phase goes to ground, now it's going to be line to line voltage, and that's why you can't use a slash rated breaker and on the delta ungrounded system. There was a question that came up about motors. How would you size a transformer supplying motors? The research that's been done by Jacob, one of our streamers who asked the question, and I made him go out and find the answer, is that there's no effect. The motors have no effect on the sizing of a transformer.